Hello everyone, welcome back to my YouTube channel. Again, my name is Rica Casabuena from EC31, and for today's episode, we will be focusing on Power-Electronics midterm exam, which is the half-wave rectifier with series inductor source load, which is our problem-solving set A in our Power-Electronics midterm examination. So this is submitted by yours truly and submitted to Engineer Emmanuel Longares, our Power-Electronics professor. So our midterm exam problem for our set A is that we will be constructing a half-wave rectifier circuit with a series inductor source load, which is supplying an AC source of voltage of 200 voltage RMS with our frequency of 60 Hz. Now, our DC source is 96 volts. So, using PSpice, we aim to determine the value of our inductance that will yield or that will give us 150 watts power absorbed by our DC source, which is our 96 volts DC source. We will be using the default diode model to make our circuit work. So to give you a heads up or a glimpse of our circuit, this is our circuit in our PSpice, and we will be considering a transient voltage sine source, a D-break as our default diode model, our inductor here, which is the parameter that the problem is asking for, that we aim to figure out, and a voltage DC source with 196 volts voltage. So our V amplitude here is 339.41 because, as you can remember, V amplitude is the voltage peak of our circuit. Since we are given a 240 volts RMS value, we have to convert it to a voltage peak value by multiplying a square root of 2 to our 240 volts RMS. With that, we can obtain the voltage peak value to be used in our circuit. So now, we will be proceeding in our ORCAD PSpice simulation. Now, proceeding with our actual circuit construction in PSpice, we will be needing a transient voltage sine source here, which will give or supply the required voltage needed by the circuit. And then we will be needing our D-break, which will represent our default diode model. And then we will be needing as well our inductor, which parameter or value will be determined using our PSpice simulation later on. So this 10 microhenries here will be disregarded later on. And next one will be our voltage DC source with a parameter of 96 volts. So let's now set the parameters of our circuit. So this one is 96 volts, as you can still remember. Okay, this is 96 volts. And then this V of here should be 0. Our V amplitude should be 339.41, just like what we've explained a while ago, because the voltage supplied is 240 VRMS multiplied by the square root of 2. It will yield us to 339.41. Our frequency is typically 60 Hz, and 60 Hz is given in the problem, and our AC should be 0. Now, let's rename our voltage sources here. So this will be voltage AC or VAC because it is the voltage supplying a 240 VRMS, and then this one is VDC because it is a DC voltage source. So let's use wire to connect our components here. Okay, wire. Then let's connect it. Let's connect the diode, and then the diode on the inductor, and then the inductor to our DC voltage source, and then going back to our VAC here. And then after that, we need the ground. Okay, we need a ground, 0 cap C. Make sure it's 0 to make sure that our circuit will be functioning well. So let's connect our ground here. Okay, so it's better if our ground will be connected to our voltage source. Let's delete this one and let's move it here, and then let's connect a wire on our ground. So this will be our circuit. And since our inductor, okay, is the parameter that we will be determining using our circuit, we will be encoding or inputting this as a variable or parameter L using our braces here. Okay, so let's put a capital L here, okay, and let's click OK. Now, you should take note of this next step. We will be setting the parameter of our inductor or our variable here, variable L here. So to place a parameter, we should click here, place part, and then we will be using, okay, from our library, we will be using special.olb library here from our PSpice file. So we should open this one. And after that, we should search here param, okay, which indicates parameter, which will allow us to set the parameters for our variable L. So let's put it here. Our parameter will be put it here, okay. After that, press escape. Now, to set the parameters, we should double click this one. And then, now, as you can see, okay, as you can see here, an editor will pop out, okay? And to edit our variable or our parameter, we should select here new property, okay, click yes, and then we should set the name to L, which is the same name with the circuit that we made a while ago, and then we will be considering the value of our inductor to 0.1 to make sure that we will be yielding to an accurate result. So let's select apply, okay, and let's select yes. So after renaming our variable L as our parameter L and setting its parameter or initial value to 0.1, we should display its value on our circuit. Okay, so let's display the name and the value so that it can be seen on our circuit. So let's click OK. So let's just click OK here and yes. And now we should go back to our schematic. And as you can see here, right, our parameters has been set automatically to 0.1 because we set it on our editor a while ago. And now, after constructing our circuit and our PSpice, we should create a new simulation profile. Okay, new simulation profile, and let's rename this midterm exam. Okay, midterm exam, and then let's click create. So there will be a pop-up here which will allow us to edit our simulation profile. So since we use a 60 Hz frequency, we should convert it. Okay, we should convert it to our period wherein t is equals to 1 over f. So 1 over 60 is 16.67 milliseconds. So that's our run to time or our period. And this is really important. In order to determine our variable L or our inductor parameter, we should use parametric sweep. Okay, this will allow us to determine that variable. We should click here global parameter, and our parameter name is L, or short for inductor. Now, as you can see on our screen, the lower part corner, we will be setting our sweep type here to linear. And with that, we will be setting the start value as well as the end value and the increment that we will be individually selecting in order for us to obtain the accurate results of the variable L or the parameter wherein the DC voltage source will deliver 150 watts. Okay, we will be determining the value of the inductor using this start and end values. So as for me, I will be using 0.22 as my start value and my end value will be 0.26, meaning I will start gathering data from my parameters using my starting value of 0.22, and I will be setting an increment of 0.005, meaning as we start with the 0.22 value, it will add up 0.005 as its increment until it reaches the end value or the final value of 0.26. So let's apply this one and click OK. Then after this one, we will be running our simulation. Okay, so let's wait for the pop-up here. Okay, so as you can see here, this available sections shows the initial value or the starting value as the increment value adds up to those values until it reaches the 0.26 or our end value that we use to accurately determine, the power that is absorbed by our DC voltage source. So let's click this OK. Then we will be adding our trace, wherein we will be measuring, we will be analyzing the parametric sweep of the average value of the power across our voltage DC source. So let's click OK. Okay. So as you can see here, this graph here, this series of graphs here shows the parametric sweep of the value of the power absorbed by our DC voltage source. So as you can see here, the y-axis here represents the values of power, from 0 to 300 watts. And this one is our period that we set, which is up until 16.67 milliseconds or 60 hertz when we convert it to frequency. So now we will be analyzing this DC sweep to know if our simulation is correct, So we are expecting that the value of the average power across our DC voltage source approaches or is near to the value of 150 watts. So now to analyze our parametric sweep, let's toggle our cursor in, cursor on. So as you can see here, these are the values of the average power across our DC voltage source. So if you will be observing, here on this graph and on these values, this light green here shows an average value of 148 watts, approximately 150. But here, the pink value of the average power is 150.877. So this value is quite acceptable, This value is quite acceptable, which proves that our simulation is correct. But if you want a more accurate value, so now to get the value, the value that we will be considering on our next simulation to get a more accurate result for our inductor value. Let's check, okay? As you can see here, this light green here, we will be checking its inductance value. So as you can see here, the step parameter L is equals to 0.26, okay? We have to take note of that value, okay? We have to take note of that. And because we will be using this value as our start or initial value on our next simulation. And for the next one, we will be considering this pink yellow here, this pink value, okay, this pink one, this 150.877 value of our DC, of our power across the DC voltage source, because it is the nearest value to our desired value, okay? So we will be checking it here, so this pink symbol here, and then we will be taking note of the step parameter L, which is 0.255, which will be used as our end value later on in our next simulation. So now we will be going back to our OrCAD PSpice. So we will be editing our simulation settings here. Okay, let's edit our simulation. We're in, just like what I've said earlier, we will be changing the value of our start value here. So we will be considering 0.26 as our start value, which yields a 148.013 power, okay, watts across our DC voltage source. And our end value will be 0.255, which yields a result of 150.877 watts, okay? And we will be using an increment of 0.001. Before, we used a 0.005, but now we will be using a 0.001 increment to make sure that our results will be more accurate than the previous one. So let's apply this one. Click OK. Then let's run our simulation. Okay, so as you can see here, these are the values, okay? So these are the new values for our definite intervals, okay? Wherein we considered a start value, okay, a start value of. So as you can see here, we set up our new simulation settings wherein the start value is 0.26 and our end value is 0.255 with an incremental value of 0.001. Okay, so let's click OK. So for another try, we will be adding our trace just like before, okay? Average power across our DC voltage source, and let's click OK. So as you can see, our graph has been compressed more than the previous graph, meaning the values are nearer to each other, okay? Yielding to accurate results. So let's toggle our cursor on and let's measure our average power. As you can see here, the cyan colored here yields to 150.844 watts, okay? Which is nearer to our 150 watts compared to our 150.877. And this fuchsia or pink, okay, pink color here yields to 150.267 watts, okay, compared to our 148 watts a while ago. So we will be using the value of these two parameters here. So let's consider the cyan color here, okay? You have to take note this value, okay? 0.255, we will be using this value as our end value on our next simulation for a more accurate result. And this pink color here, which is our starting value for our next simulation, okay? 0.256, okay? Which yields to 150.267 watts, which is almost near to our 150 watt expected result, okay? So let's click OK. Now for our last simulation, okay, wherein we will be obtaining the most accurate value of our inductor that will yield 150 watts power absorbed by our DC source. So let's edit our simulation settings here. And as what I've mentioned a while ago, okay, we will be considering the value we got from this simulation, okay, so this one, which gives us nearer value to 150 watts compared to the first simulation, okay. We will be using our start value, okay, just like what I told you to take note a while ago. So we will be using our 0.256 as our start value, and that yields 150.267 watts power across our DC voltage source. And our end value will be 0.255, which yields 150.844 watts. So to make it more precise and more accurate, we will be using an increment value of 0.0001, okay, which gives us more increment values and more accurate and precise values of the variable L, which will be giving us the final value of our parameter L, okay, that will yield to 150 watts. So let's click apply, then let's click OK, and then we will be running our new simulation. So as you can see here, the start value is 0.256. As you can see here, our start value is 0.256, and we added a 0.0001 increment value until we reach the value of 0.255, which is our end value. So let's click OK, and then For the last time, we will be adding the average power, okay, the parametric sweep of the average power across our voltage source. So as you can see here, this is a more precise and more accurate output waveform for our power across our DC voltage source, okay. All of the graphs reunited or has been compressed to a one output waveform, okay, and it has been uniform compared to the last two previous output waveforms. So we will be toggling our cursor on for our analysis. So as you can see here, we are given a lot of values, okay, a lot of values of our power, because we use an increment of 0.0001. So this gives us a more accurate value wherein, as you can see here, the nearest value of the average power to our expected value of 150 watts is this one, 150.051 watts, okay? So this yellow value here will be the value that we will be considering as the value of our inductor L. So this one, this triangle here, okay, let's check this value. So as you can see, the value for our step parameter L is 0.2557 henries. So we will stop here with our simulation because we almost reach the average power, which is 150 watts. So the value that we will be considering for our inductor will be 0.2557 henries. So that's our midterm examination. I hope you learned something from our experiment today, okay? But before that, let's first test if our 0.2557 henries is correct, which will give us 150 watts approximately power across a DC voltage source. Now, testing the correctness of our result, okay, we will be changing the value of our inductor here, okay. We will be deleting the inductor that we used a while ago, and then let's delete this parameter, and then let's place another inductor here. Okay, piecewise component and then inductor, and let's place it here, and then we will be using the value, okay, we will be using the value that we have solved using piecewise, so that's 0.2557. So let's click OK, and then let's edit our simulation settings. Let's untick parametric sweep, and let's just consider general settings here. So let's click apply, and then let's click OK. Now we will be running our simulation, okay, to test if our 0.2557 is correct. So let's add our trace, okay, average power across our voltage DC source, okay. So as you can see here, this is similar to the output waveform we just obtained on our third trial during using our parametric sweep. So let's toggle our cursor on, okay. So let's measure the average power across the DC voltage source. So as you can see here, we recorded 151.385 watts, okay. This is expected because it is noted that we do not have, okay, we do not have a perfect system. So probably on this circuit, when we connected our inductor with the 0.2557 inductance, there might be a possible loss in the system. That's why there's just a small difference in the values. But the small percentage difference is acceptable with our obtained value using our parametric sweep and piecewise. So that's our midterm exam in power electronics using our piecewise software and our parametric sweep function in piecewise. So I hope you learned something from our episode today. I hope I will be seeing you on our next vlog. So again, I'm Rica, and thank you, and may God bless us all.